Oh, oh, hi there, everybody. Huh, I was just playing a little space penguin there. Hey, welcome. And this is the third and final installment of our ISN review. And so I thought I'd pick it up where we left off last time with the dead old farts of astronomy. We were looking at some of the B questions with Big Idea B. And so just to quickly review, you should have some pages in here with some dead old fart notes. You should have 3 facts for each dead old fart, timeline that goes with that, and of course we did information on the Library of Alexandria, which of course was reviewed in the previous video, so I don't need to go over that. And of course you also have a page for your paradigm video that we watched with all the different definitions of paradigm, paradigm effect, paradigm paralysis, paradigm pioneer, and then of course geocentric and heliocentric paradigms. Which I don't need to remind you, of course, are different views of how we think the Earth and the Sun interrelate with each other. That's all Big Idea B stuff. We really want to move on to Big Idea C. So we're going to move past the McMillicentric universe and look at our Big Idea C and our C questions. So C1, how do objects move in outer space? Of course, that has to do with Newton's laws. We spent a crazy day, if I remember right, on a late start day, and it was homecoming, and we reviewed Newton's laws, which you learned back in 6th grade. The first law says an object tends to stay at rest or in motion unless acted upon by an outside force. The second law says that force equals mass times acceleration. And then, of course, the third law, for every action, there's an equal and opposite reaction. Every bully's worst nightmare, that third law. So we spent a good chunk of that day just doing stupid human tricks and having each person demonstrate one of Newton's laws in front of the whole class. So you can just put that in there on the right side, and that takes care of it. You don't need to do a right-sided activity because flopping around on a table, for example, is a creative act. And so there you have your right-sided activity. C2, how do Kepler's 3 laws of orbits work? And more importantly, why do we care? And that really is a 2-pager as well. The first page would be the Harmony of the Worlds video sheet, which you can put in on the left side. And if you recall, I was suggesting you do a movie poster on the right-hand side. You think of all good movie posters, and they always show like the hero in the middle, and then some other characters kind of surrounding them, and different scenes playing from the movie. So I could imagine Kepler here, and maybe a picture of his mom being in jail for witchcraft. Some of his ideas up here for orbits. Maybe Tycho Brahe is over here with his gold nose. You get the picture, but kind of summarizing Kepler's life. And more importantly then are Kepler's 3 laws, which do end up having quite a big impact on us. And you can see I've got little animations here to kind of go with them. Kepler's first law, planets move in an ellipse, which is just fancy for an oval shape, with the sun off to one side. And you can see that in this animation here. So the real key thing here are 2 things. It's not a circle, it's an oval. And the sun's not directly in the middle, it's off to one side. The second law that Kepler came up with was this one: planets sweep out equal areas in equal amounts of time, which on the face of it seems to suggest that if you see in this animation here, all these pi wedges are the same area, and so it takes the same amount of time to sweep through each one. But the cool thing is, if it takes you the same amount of time to sweep through this little thin wedge as it does one of these really large wedges over here, that forces a planet to change its speed. It's got to go much faster over here to cover this large area here in order to go through that same area over here where the wedge is much thinner and the distance is much shorter. So the planet goes slower over here and faster over here. And that's really the essence of the second law. The third law is that planets orbiting closer to the sun move faster than planets further away. And so you can see right here, a planet closer to the sun is going to travel faster than the one further away. So it's always comparing one planet to the next. And since you did all that hard work on Kepler's cartoons and probably doing some redos in many cases, that can go right here once you get that complete and graded and back from me. Then that would take us to C3, which would be our next page. Why don't planets crash into the sun, and why do they orbit the sun instead? And if you recall, this is where we took a lot of what Newton and Kepler both did and put them together to make sense. So we know gravity, for example, is a force of attraction based on mass. And if you have mass, you have gravity, and the more mass you have, the more gravity you have. So the sun has gravity, the Earth has less gravity, and so the sun should be pulling the Earth straight into it because of gravity. But there's something that's keeping the Earth in this orbital path instead. Instead of crashing into the sun, we're going over here instead. And what Newton finally put together is that there's another force, a second force, And he identified that as inertia, the tendency of an object to keep going in a straight line, unless it's acted upon by an outside force. That's all Newton's first law. And so an orbit is really a combination of these two forces that are kind of in a tug of war with each other. And planets don't crash into the sun because these two forces are perfectly balanced, and that creates a stable orbit. So likely this is what you'll have on your left side of your notes. You need to figure out what to do on the right side. My suggestion at the time in class was come up with a cartoon where gravity is one character and inertia is another character, and they're arguing back and forth about who's really the one responsible for orbits. And you can have them argue and try to come to terms with it, and maybe at the very end they figure out that it's the two of them together. Then we move on to C4. And C4 and C5 and C6 all came out of like a day, day and a half classroom activity where you became the teacher yourselves. And so you remember we had a globe set up in the back of the room with a light set up, and then you could measure the temperature off of the two different areas. One was at the pole and one was down by the equator. And probably what you found out is that the temperature at the pole was about 5 or 10 degrees less than the temperature on the globe was at the equator. And so why is there a difference in temperature? That's because sunlight's coming in and hitting the globe at a different angle. For example, here it's coming in much more straightforward at the equator, but coming in at a much lower angle at the pole. Excuse me. So that means then that the whole planet does not get an equal amount of radiation. And so according to the sheet here, you can circle which ones are getting more energy and less energy from the sun. Of course, the North Pole over here is getting more heat, and the South Pole is getting less. So it's got to be summer here and winter here. And the big realization then, of course, is that it's the tilt that's causing the seasons and not our distance from the sun or our speed, either speeding up or slowing down. So while it might seem like Kepler was right, he's not the one, or his laws are not the one that's responsible for the seasons. It's the fact that the Earth is tilted about 23.5 degrees, which means part of the planet's getting more heat and part of it's getting less as it travels around the sun. So then you'll have a right-sided activity, very open-ended in terms of what you want to put in for that. The second page, or the next page here, would be C5. Why does the moons keep changing shape each night? Why do we go through phases? And if you recall in class, we had an activity where we had the active board set up, and you could manipulate and move the moon around the Earth in different locations, and you could see it's a new moon over here and a full moon over here, and as it goes around, we go through different phases. First a crescent, then a first quarter, gibbous, full moon, and then it goes back again to a gibbous, third quarter, and then finally a crescent again. And so you should have a right-sided activity that can go along with that. And then finally, C6, what are eclipses and are they dangerous? And for an eclipse, really, this is where we just hit the books. And you looked up a few pretty straightforward definitions. What's the difference between a lunar eclipse and a solar eclipse? The big difference, of course, is that a lunar eclipse is when the Earth casts a shadow on the moon, whereas a solar eclipse is when the moon casts a shadow on the Earth. It's all about who's casting a shadow on whom. So for example, I could even demonstrate it here in this diagram. If we're looking at a solar eclipse, you can have the sun right here, and then the moon would be right here, and it's going to cast a shadow somewhere on the Earth. And that would then therefore be a solar eclipse. From this person's vantage point right here, they're seeing the whole sun being blocked out by the moon. And then of course for a lunar eclipse, you have the sun over here, and the moon is over here, and of course it's the Earth's shadow which is being cast onto the moon, so it appears as if the moon is going dark. It's not really dangerous. It's not really, well, it might be scary depending if you understand or don't understand these things. Certainly it scared a lot of our ancestors back in the day. But really it's just shadows and who's casting a shadow on whom. And of course the lunar ones are much more common because it's a lot easier to see a lunar eclipse because half of the planet on the night side here can see the moon cross into the shadow. To see a solar eclipse, you got to be living right here on this spot in order to see that. So those are more rare. And that really wraps up then big idea C. And of course, when you put all these different things together, the big idea that we eventually came down to was that we stand on the shoulders of giants, just like Newton said. And that all of these different things, Newton's laws, Kepler's laws, go a long way to change our lives, directly through some of the things that we enjoy, like internet, cell phones, satellite TV, cable TV, texting, and Facebook, and all those kinds of things. They all happen because we understand orbits and we can put things in like satellites into orbit and have all these great things. So one person can change the world for a better. And everything that we know and do today is really the result of people who came before us. So that wraps up Big Idea C. Hopefully the review was helpful to you and at the very least helped you to kind of square away the last few pages of your ISN. So I wish you luck on your right-sided activities. I'm hoping that they prove to be valuable to you and that helps you to understand the concepts a little bit better. And I can't wait to see them here in a few more days. So best of luck to you all, and we'll see you on the flip side. Have a good weekend, everyone.